Hello and welcome back. In this video, we apply the conservation of linear momentum equation to a fluid flowing through a nozzle. Consider the linear momentum equation again, we derived using the Reynolds transport equation. Let us review the meaning of each term. Sigma F is sum of all forces acting on the system. The next term is the time rate of change of linear momentum of the system within the control volume. And the last term is the net flow rate of linear momentum through the control surface. The forces acting on the fluid system are the body forces due to gravity, the surface forces due to friction, and the pressure forces. In this video, we will apply this momentum equation to a simple flow system such as nozzle flow, and arrive an expression for thrust developed. Consider steady flow of a fluid through a converging nozzle, fixed on a stand as shown in figure. The goal is to derive linear momentum equation, and to find the thrust developed on the stand, when fluid flows steadily through this nozzle. Assume the flow is incompressible. Consider two locations 1 and 2 where cross-sectional areas are A1 and A2 respectively. The first step is to identify an appropriate control volume, so that we can imagine that the system or fluid is flowing steadily through it. Using continuity equation, we can derive an equation for conservation of mass of fluid flowing through this system. We have seen that mass flow rate will remain same for steady flow at each area of cross sections. Now consider the momentum equation. Since the flow is assumed steady, this can be simplified to equation 1. The right-hand side of equation 1 can be further simplified. For control surface 1, since N1 and V1 are constant across this surface, we can simplify the surface integral equation to minus m1.v1, where m1 is the mass flow rate through the surface 1. Note that N1 and V1 are opposite in directions. For surface 2, the integral can be simplified to m2.v2. Substituting these back to the momentum equation, we can simplify equation 1 to 2. In equation 2, sigma F system is sum of all forces acting on the system when it is flowing through this control volume. In this case, the force acting on the fluid system is in the positive I direction. Therefore an opposite reactive force will be experienced on the control volume fixed on the nozzle. To balance this force, a reactive thrust of same magnitude will be developed on the stand. Water is steadily flowing through a nozzle section as shown in figure. Calculate the mass flow rate through the nozzle and velocity at location 2. Also calculate the thrust developed on the stand. Considering fluid as a system, and using an appropriate control volume analysis discussed earlier, we can derive an equation for conservation of mass and momentum for the fluid flowing through the nozzle. Since velocity and area of cross-sections are given, we can calculate mass flow rate of water at section 1. Using this mass flow rate we can find velocity of flow at location 2. Finally, using the thrust equation derived for this stand in the previous section, we can calculate the thrust developed. Consider another problem. Water flowing steadily through a nozzle at a rate of 1 kg per second, impinges a curved surface with a velocity 2 meters per second, and deflected 180 degrees as shown in figure. Calculate the force exerted by the fluid on the surface. Assume the speed of water remains the same during deflection. Considering fluid as a system and using appropriate control volume analysis discussed earlier, we can derive a momentum equation for the fluid flowing through the nozzle. We can show that force acting on fluid system is in negative direction. Therefore the reactive force will be on positive x direction. The magnitude of force exerted by fluid on the surface is m dot times v1 plus v2. Since the speed is same, the thrust will be 2 m dot v1. Consider another problem. A water jet is striking a fixed plate as shown in figure. The average velocity of water at nozzle exit is 20 meters per second. Mass flow rate equals 10 kilograms per second. Calculate the force needed to prevent plate from moving horizontally, due to the impingement of water stream. Consider steady flow momentum equation. Considering the fluid as a system and, using appropriate control volume analysis discussed earlier, we can derive momentum equation for the fluid impinging at the surface. In this case, we have three control surfaces where fluid cross the control volume. We can show that the x component of force acting on fluid system is in negative direction. The y component of force will cancel out, assuming that the vertical velocity of flow, v2 and v3, are same, but opposite in direction. Therefore, the reactive force acting on plate will be on positive x direction. The magnitude of force exerted by fluid on the surface is m times v1. Using this equation, we can calculate the thrust developed. Water is deflected 30 degrees using a rigid surface as shown in the figure. The velocity of water entering the deflector is 1 meter per second. Assume the speed of water not changing during deflection. The mass flow rate is 2 kilograms per second. Calculate the reactive force exerted in x and y direction. Also find the resultant reactive force. We will solve this problem in class. Thank you for listening.